In this video, I'll go through some examples of calculating determinants for 2x2 and 3x3 matrices. So for a 2x2 matrix, A11, A12 in the first row, A21, A22 in the second row, the formula for calculating the determinant is A11, A22 minus A21, A12. So it's the elements on the main diagonal multiplied together, subtract the product of the elements on the off diagonal. So let's run through some examples. So for this first example with minus 3, 1, minus 4, 2, we'll multiply minus 3 and 2 to get minus 6, and then we subtract minus 4 times 1, so subtracting minus 4 is the same as adding plus 4, so we get minus 6 plus 4, so that equals minus 2. Second example, minus 1, 2 in the first row, 4, 2 in the second row. We've got minus 1 times 2 gives us minus 2, and then subtract 4 times 2, which is 8, so we get minus 10. And then the third example, got minus 1, 2 in the first row, 2, minus 4 in the second row. Got minus 1 times minus 4, which is plus 4, and then subtract 2 times 2, which is also 4, so we get 0. Moving on to 3x3 matrices. So if I write the matrix in this form, so the general convention with writing the elements of a matrix, the first number in the subscript is the row number, and the second number is the column number. So we've got A11, A12, A13 in the first row, A21, A22, A23 in the second row, and A31, A32, and A33 in the third row. So the formula for a determinant for a 3x3 matrix looks quite a bit more formidable than for a 2x2, but really it's just replicating the 2x2 formula and then multiplying, and we've got a pattern of pluses and minuses to worry about as well. So let me just go through what the formula means. So if we're expanding along the first row, and it turns out we can expand along any of the rows, but for the sake of argument I'm just going to expand along the first row. So you first of all take the first element here, A11, and then imagine blocking off that row and that column. Then you're left with a 2x2 matrix here. And so what we do is we calculate the determinant of that matrix, that 2x2 matrix, and multiply by A11. So that's essentially what this first part of the formula is. And then we go to the second element in the first row, A12, and we imagine blocking off that row and that column, and we'll be left with another 2x2 matrix. So we calculate the determinant of that 2x2 matrix, so that would be A21, A33 minus A31, A23. And we multiply by the negative of this element here, A12. So that's what this is here. We've got minus A12 times the determinant of the 2x2 matrix that's left when we eliminate the first row and second column. And then the last piece is move into the third element in the first row, block off the first row and third column, and you're left with this 2x2 matrix in this part of the 3x3 matrix here. Determinant A21, A32 minus A31, A22, and multiply by that third element in the first row. And the pattern here is plus, minus, plus, because we're expanding along the first row. We can also expand along the second row, in which case you would perform the same kind of approach, but the pattern of the pluses and minuses becomes minus, plus, minus. And then if we do the third row instead, we're back to plus, minus, plus. We'll see an example of that in I think the third example below. So let's work through those examples. So first of all, I'm going to write down the first element in the first row, and then I'm going to calculate the determinant of the bottom right 4 elements. So blocking off the first row and first column, I'm left with the 2 by 2 matrix 4, minus 4, 4, 1, and so the determinant of that would be 4 times 1 is 4, minus 4 times minus 4, so minus 16 is plus 16. And then move to the second element in the first row, and we have a negative sign now, and then block off the first row, second column, and we're left with the matrix that has 1, 1 on the main diagonal, so 1 times 1 is 1, and then 4 and minus 4 on the off diagonal, so minus 16, so plus 16. And then finally, if we move to the third element in the first column, that's a 4, and now we're back to a plus. And if we block off the first row and third column, the matrix we're left with, the 2 by 2 matrix we're left with, has 1 and 4 on the main diagonal. So multiply those together, we get 4, and then subtract 4 times 4 on the off diagonal, so we get minus 16. And so what have we got here? We've got 2 times 20, so 40, and then we got minus 2 times 17, 34, and then we've got 4 times minus 12. Okay, so what does all that come to? Testing my mental arithmetic powers here. Let's combine the 34 and the 48 first, because they're both negative, and we'll just leave the 40 alone for now. I'll do this in 2 steps. So 34 and 48 would be 82, and then 40 minus 82 is minus 42. Let's move on to the second example. So again, I'll expand along the first row. So we'll have 2, and then we've got 16 plus 32, and then we've got minus 2, moving to the second element, and we'll have 4 plus 20. And then moving to the third element, we're back to plus, and we've got 8 minus 20. Okay, so what do we got? We've got 2 times, actually let's just do this in 1 step, otherwise I'm going to run out of room. We got 2 times 48, so 96. And then we got minus 2 times 24. And then we got 4 times minus 12, so another minus 48. Hey, look at that. We get 0 for the determinant. I haven't really said anything about the purpose of determinants, and that's because the focus here is on just calculating determinants, but determinants are useful for all kinds of topics in linear algebra, and in particular if you get a determinant of 0 for a matrix, that leads to interesting things. Okay, let's do the third example. And remember I said we could expand along any of the rows? If we expanded along the first row, we've got non-negative numbers all the way along the first row, and so we're going to have 3 calculations just like we had up here. But if we're a little bit attentive, we can see we've got 2, 3, 0 in the second row. So that 0 means that the third calculation is going to be 0. So it shortens the calculations we have to do if I expand along the second row. I could also expand along the third row because that's got a 0 in it as well. But for illustration, I'll expand along the second row. Okay, so here we go. Let's start with 2. And remember I said if you expand along the second row, the pattern, instead of being plus minus plus, it's minus plus minus. So that 2 in the second row is going to be minus 2 now. And then what's left is, let's just make sure that you can see what's left. So I'm expanding along on this point here, so I'm going to exclude this row and this column, and I'll be left with these 4 elements here, the 2 and the minus 1 and the 2 and the 3. So 2 times minus 1 is minus 2, and then I'm going to subtract 6, 2 times 3, and then next element on the second row is a 3, and remember my pattern is minus plus minus, so this will be a plus. And what's left if I eliminate the second row and second column, I'll have the 4 corner elements. So I'm going to have minus 4 times minus 1 is plus 4, and then 0 times 3, that's just 0. So, and then the last piece is 0, because I'll multiply 0 by a determinant of a 2 by 2 matrix, and that's just 0. So I don't even need to worry about doing any calculation there. Okay, so this calculation ended up being a bit shorter than the others. That's because of the 0 in the row that I expanded along. I've got minus 2 times minus 8. So that'll be 16. And then I've got 12, 3 times 4. So that's 28. So there's a few examples of calculating determinants for both 2 by 2 matrices and 3 by 3 matrices.